Good morning. Let us continue our discussion. So what were we discussing in the last class? Did any of you remember? What is that we were discussing in the last classes?
We were discussing about various computer vision tasks, and our last discussion was based on depth estimation and 3D reconstruction, where we established the relation between depth and disparity.
Very good. So we were discussing about 3D reconstruction in general, and then we said that there are different monocular and binocular based depth estimation methods. 3D is essentially the depth information, because 2D we have the image information. We can spatially understand. If we can map the pixel information to the centimeter or mm information of the real world, okay, in 2 dimensions, we can understand the location of the objects in 2 dimensions. But however, the depth information, say for example, if there are several objects in the scene, okay, which object is where in, how far is it from the camera? That information is not there in a image. Directly, it is not there in an image. So there are some methods to extract it or infer it from the images. There are some methods which are texture-based methods, as I mentioned. Say if I show like this, so you're able to see that there is a depth information already here. Okay, and even say if I am just showing like this, if I take a couple of frames, you can estimate what is the depth roughly, because there is a motion. This motion also will help us to understand what the scale of the object is. Okay, and then based on the scale of the object to get the depth as well to some extent. So similarly, texture will help, even the focus, defocus, blur, all these are monocular cues or monocular clues for depth estimation. Monocular means from a single image, how do we estimate the depth? While it comes to the absolute depth estimation, that is, if I want to know exactly how much distance in mm or centimeters or meters it is far off from the camera, then we need 2 images. Okay, relative depth is easy to obtain or somewhat reasonable to obtain from the monocular images, so from a single image. However, if you would like to get an absolute depth, we need a 2 images, like human eyes, how they look, and grab the 2 images of the scene. Using these 2 images, we can extract the depth information in stereo-based methods. That's what we discussed in last class. So just to have a recap quickly, and also to get the further understanding on the depth extraction or 3D reconstruction. Okay, so what did we derive in the last class? If we have a scene point, assume that there is a scene point here. Okay, so assume that there is a scene point here. Some objects. Okay, so these are the objects seen from the images or from the camera. Then what will happen? The same object will have actually its projections at different. So assume that these are the cameras. Okay, these are the cameras, and say the projection of the scene point in the left image is here. Okay, this is the left image and this is the right image. Projection of the scene point in the right image is here. Okay, so that's what can happen, because I'm looking from 2 different views. Okay, when I look at the same scene point also, even though I'm looking at the same scene point, the cameras at different locations. So I'm looking at from the 2 different views. So as you can see here, say this is the coordinates corresponding to this. If I say that xl comma yl, and then the coordinates corresponding to this projection or xr comma yr, then what did we discuss or what did we derive in the last class? Can anyone tell? What is that? I want to know the depth information, that is how far from the cameras. These are the cameras. Okay, this is the scene point. I want to know how far is this cameras, okay, are these cameras from the scene point. Okay, assume that this is what we want to know. These are at the focal plane. So usually what happens is the image happens in a camera. The image gets formed at the distance of a focal plane, okay, from the camera. And usually what happens is the formed image behind the camera is an inverted image. That means if I have an object like this, okay, what the image gets formed is like this. Okay, so it's an inverted image. So instead of like this, it will form like this. So behind the camera. So we can, it is customary to assume the image plane at the distance of say focal length distance behind the cameras or in front of the cameras also sometimes. They make the without inversion, they assume that the image is formed without inversion in front of the camera as well sometimes. Okay, so and then these are the cameras. These are separated by some distance referred to as baseline. Okay, and then this is the focal length. Usually focal length will be small, baseline will be even higher. Okay, and the focal length will be little smaller than baseline. And what is even more bigger is the distance of the scene point from the, if I denote it with capital D, okay, distance of the scene point from the cameras will be even further. Okay, I have not depicted very well in this image, but usually what happens is the distance, okay, will be much much higher usually than even the baseline, and as well as the disparity. Okay, so now what did we discuss in the last class? So if we have, this is the camera setup and then the image formation and then this physical scene point, okay, P, whatever. Okay, and what did we discuss in the last class? Can anyone tell? What did we discuss in the last class? Depth, how do we get? Depth information, D is equal to, what did we derive? Baseline into focal length by disparity. Okay, so if I denote with small d disparity, see if the cameras are positioned horizontally, that means on the same horizontal plane, then what happens is the shift also only in the horizontal plane. So previously, if, okay, let me just try to see. If these coordinates are, so shift is now, assume that this is the shift. Okay, so previously the coordinates are here, assume that, and then now it is shifted like this. Okay, so the shift is also horizontal, and hence both, say if I consider this as y and this as x, okay, then the shift is xr minus xl. Okay, this is the disparity, right? That's what we have derived in the last class. Okay, so essentially capital D is equal to BF by small d. So it is a function of both baseline, focal length of the cameras, and then the disparity. So now if I want to estimate D at all locations, at all x comma y, what is the x comma y spanning over? In the range, what? What is the range of x comma y? Oh, it can be either 0 to m or 1 to m and 2 to n. Okay, sorry, 1 to n. So if we image, if let's write x and y. Okay, what does m comma n denote? Oh, so the image dimension is m comma n. Okay, so if I would like to find the distance at each of the locations, see, because see at each location some scene point will be there. So if I see virtually there will be scene point, it will be like this. Okay, here also you can see that same thing may happen. So some part may or may not be there as well. Okay, it's not necessary that the whole what we see in the left image will be there in the right image. Okay, sometimes both will be there. Okay, the projections will be there both in left and right images. Sometimes it may not be there. Okay, but if I want to calculate the depth information, okay, for which locations are, what is the mandatory requirement? The object has to be there both in left and right images. Okay, if I don't have the object in the right image or left image, object information or projection of the object in the right or left images, then for those points, I will not be able to calculate the disparate depth information. Okay, and this is equal to what? V, is it a constant or not? With respect to x, it is
constant.
F are constants with respect to x comma y. Which is variable with respect to x comma y here?
The disparity, the shift.
Disparity or the shift. Now the question is, how do I find d of x comma y? To find out depth. Okay, the question is how to find small d of x comma y. Okay, for all x comma y. How do I find it? Can any of you answer it? How do I find it? Found by what? By, see, at each location, say for example, here I have shown only one object or some scene points. See, there may be some other objects here. Okay, here also there may be some other objects. Remaining places, if there are no objects, it's fine. Okay, no need to find depth at all, because that's the reference plane you can assume. Okay, and now wherever there are objects, I would like to find out the disparity now, d of x comma y. What should I do for that? Any answer for that? What is that?
Like you can take only the corner points of the objects and then you can find the shift in the corner.
Okay, so one way is find out the corner points in the objects of the objects. Okay, and then find out the shift, okay, of the objects from left image to right image. So what essentially we are doing is we are trying to establish a correspondence, okay, between the feature points. Okay, identify the key points. And then establish correspondence. What do we mean by correspondence? What?
Matching between them.
Huh?
Matching between them.
Yeah,
It is the same point.
template matching. Yeah. It can be through template matching. Or template matching, or what else I can do? So if I want to see if this is scene point is same as exactly that scene point or not, what else I can do? I take a patch around this, and then what I do? What should I do to find out the corresponding point?
Take the features of that point and
Yeah, take the features of this, take a patch. How to establish correspondences? Okay, and then its features. Then what should I do? To find correspondence, what should we do? Take a patch. Okay, take its features, and then what should I do? After taking features, what should we do? Then
try to find for which point the feature matching is the best.
right, to which point the feature matches I have to see, but where should I see is the question. Should I see all across the whole image? For this, say for example, this point I want to find. Okay, this point, say let it be 10 comma. Okay, x, y, sorry. X is maybe okay, this point let it be 100. No, x is 100 and y is 10. Okay, assume that 100 comma 10 is the point for which I want to establish the correspondence. Okay, then what should I do? Where should I search? I should search on
Same x-axis.
but for all x, is it not? I have to search, I have to take a patch here, take a patch here, take a patch here, okay, and so on, all these patches. Is it not? Among these, which is the best patch I have to see? Is it not? So I take its features and then search for a match on all the points of that row. Correct or not? That column here. Okay, so if we consider this as X and this as Y, I think, okay, on that row, fine, let's go with this. Okay. So is it necessary? The question is, should I look even the whole row? That means at each, say in this row, at each column, should I see for the correspondence, or can we still simplify the search region? Is there a feasibility to still simplify it? Usually what happens is, see, we assume that the object, we know the rough range of the distance in which the objects are in the scene. We know its range. Okay, if its range is, say, for example, say if I am considering from a reference being 0 depth, okay, and then to 2 meters. So roughly I know that all objects are in 2 meters distance range. Based on this range, I can set the range for this. So the range for this, if I say that it is only 0 to 30, okay, then what do I do? If it is 0 to 30, I will only search around 30 pixels, okay, from this pixel. Okay, I will just try to take 100,10 here and then 100,130. Only up to that I will search. If I know that if this distance is -1 to +1, okay, then what I search is from -15 to +15. Okay, pixels. So this is the range in which I search. This we call it as the search range. Okay, so we will see with the camera geometry when this is valid. Okay, so there are some terms like epipolar plane, okay, epipolar lines, and so on. I will discuss that with the with some images. Okay, essentially the plane passing through the cameras and the scene point is referred to epipolar plane, and the projection of any scene point will only be in the epipolar plane. The epipolar plane that cuts the image planes are referred to as epipolar lines. Okay, so each of the image planes will be cut by this epipolar plane at a line. Okay, so these lines are called epipolar lines. So I will just show with some illustration and then discuss on that. So the search is usually constrained on this epipolar lines only. For any scene point in like left image, if you want to set the corresponding point, okay, the projection of the same point in the right image, then where we need to search is only on the epipolar line corresponding to the point. Okay, so that we will see little more detail with illustration. Now here these epipolar lines are now nothing but the horizontal lines, because the image, the cameras are placed horizontally. Okay, and then any scene point will be seen on the same row here. Okay, so is this clear? Any questions on this now? Okay, if this is clear, then what we said is, if we have a any key point, okay, if you want to identify a corresponding point for this, what you need to search is from the same point, okay, around in the set space, okay, in the same row. So if I consider again this as y and x, okay, on the same y equal to here probably maybe 130 or whatever, okay, and x equal to, so if this x equal to 150, well, where we search is, okay, 150 minus probably 10, okay, and then 150 plus 10. Okay, plus 10 or minus 10 is decided by whom? The range of the depth, okay, or the range of the disparity. Okay, that's what determines whether how many pixels should I search on that row. Okay, so the plus 10 minus 10 to plus 10, okay, is determined by what? Disparity range. Okay. So now the question is, how do I perform mathematically? See, looking at each, so you need to perform template matching, and I try to see, okay, where it is most closer. Is it not? That's what we mean by template matching. We will put a patch here. Okay, you will put a patch here. Okay, and then put a patch at every location in this, at each pixel. Okay, in this window, and try to see which window, okay, or which, at what location this patch is most similar to the patch in the right image. Okay, so we should have a mathematical framework for guiding it. So I would like to define a cost function again here. Okay, the cost function here is, so I can either denote with whatever, J or whatever, or L also. So how do we want to define it? Is set at each x comma y, I have to find out. Fine. But what I want to see is, I want to see if this is IL, right image is IL. Okay, and then the left image is IR. What we want to see is IL of x comma y. Fine. How close is it to IR of x comma x plus u comma y plus v? What is this x plus u comma y plus v? What are u and v's? Can you tell? What do you think is u and v?
From minus 10 to 10.
Minus 10 to 10. Okay, so essentially the cost function now is a function of u and v, because for which u and v it is smaller. That I want to see. Okay, the cost is smaller. Yet each x comma y, I want to see this. Okay, in fact, it is also a function of x comma y, but essentially we explicitly represent u comma v. Okay, the reason being, for each u comma v, I will see. Okay, and minimization essentially happens for u comma v. Okay, x comma y at a given point is a constant. Now, what should I do with this? I have to find the difference. Okay, I have to formulate the cost function. What should I do? Is this difference enough? Is this difference enough? Huh? So sometimes the IR may be higher, IL may be higher. Okay, so how do we take care of it in cost function?
Squaring.
What is that?
Taking the square of the difference.
Square of the difference, right? But if I take just at x comma y and try to see, is it a better match? X comma y versus x plus u comma y plus v, is it a good strategy? Is it a good strategy? So I'm just trying to see if this point is closest to this point, or this point, this point. Should I look the closeness with respect to the point, or a patch around the point?
Patch around the point.
So how do I account it in the equation or expression?
Summation over a window, neighborhood of.
Summation over a window. So I will put a window with I comma j. Okay, and then the summation over I and j. I and j belongs to neighborhood of x comma y. Okay, so essentially I comma j belongs to neighborhood of x comma y. There may be, say, essentially writing I equal to x minus some 5x minus 2 comma x plus 2. Okay, and j may be y minus 2 to y plus 2, something like this. So essentially this we denote it as the neighborhood of x comma y, to while writing simplify, because sometimes x minus 5 comma y, like we can consider the neighborhood as 2 cross 2 patch around the point, sorry, 3 cross 3 patch around the point, 5 cross 5 patch, 11 cross 11 patch, and so on. Okay, it's up to us how much neighborhood we consider. Okay, and then this is referred to as sum of square difference error. For what? For finding correspondence. And hence, see, but if I know that the cameras are placed only horizontally, what simplification can I do? So what I want to minimize here? So this has to be minimized with respect to u comma v to find out u star comma v star. Okay, what are the corresponding points? is denoted by u star comma v star while minimizing L with u comma v. Okay, is this fine or not? Now, if I know that the cameras are placed only horizontally, exactly on the same horizontal line, what simplification does it lead to?
We have to only see it for U star.
We only need to find V star. Okay, because U assume is constant. Okay, for all of them. And V star is just minimized. So you need to search for a given U. That means even say U equal to 0. Placement, we consider U equal to 0. Okay, no need to search for all different rows. Okay, just search for different columns. That's all. In fact, even though it's a function of u comma v, we can consider only a function of v. Is this fine? So this simplifies greatly because instead of, say, if I want to find out a corresponding point, say, even if I consider -10 to +10 range, how many comparisons I have to make? If the patch is 5 × 5 as we considered here, okay, to see whether the corresponding point for a like at a given x comma y, how many comparisons or how many computations do I need? How many computations total do I need at a given location to see whether it is a good match or not? Okay, how many computations I need? This 5 × 5 patch. I just want to tell the mean square error between this patch versus this patch. How many computations do I need? How many computations we need to find the mean square error? Number of computations means what? Number of additions, multiplications. Okay, those are considered as computations. So 25 pixels are here, 25 pixels are here. You are finding element-wise subtraction. Okay, and hence 25 operations you are doing, and you are squaring the error and then adding up. Again, 25 additions you are doing. Okay, and then 25 square. So you are doing essentially order of 25. Okay, because 25 is the number. Okay, 25 into 3 or 25 into whatever. Okay, so it's order of. Okay, or if neighborhood is from -n to or minus yes to yes. Okay, so then order of yes. Okay, now this is at a given point to like patch to patch matching. How many patches should I consider to declare that the one of the point is a corresponding point for this? How many patches should I consider? So if the disparity range is -2 to 10 here, okay, how many points should I consider? If disparity range is d min to d max, okay, so d range, if I am given, that is d min minus d max minus d min. Okay, if this information is given, sorry, this information is given, how many comparisons should I make? So order D range into S computations. Okay, for establishing yet one point. Okay, and how many xy will be there? Usually, not necessary to find out only at the corresponding points. Okay, there are some methods, as I mentioned, sparse depth estimation methods, which only find at the key points. But usually, it is necessary to find the correspondence at all the points in the image, left image to right image. So it is for each x comma y. If I want to find establish the correspondence, total computations are How many? Order of, this is the order of, okay, order of means it can be 10 times, 5 times, okay, something like that. Less than, roughly less than 10 times we consider. Order of D range into S into M into N. Okay, so these many, say Mn is 100 cross 100, or like D range is say 20, and then S is 20. Okay, so 400 into 100 cross 100, 10 power 6 operations you have to do. Okay, to see whether the to identify the correspondence. Okay, at a given scene point from the two images. Oh, these many computations are needed. So it's not very easy task. So this is with this square function, sum of square difference. Okay, sum of square difference error. Okay, there are different other metrics or cost functions you can consider. What is the other cost function you can consider? Instead of sum of square difference, sum of absolute difference you can do. Okay, so that also will give some kind of estimate how close they are. Correlation also you can do. Normalized cross correlation between these two also you can do. Between these two, we want to see the match. Okay, so you can do any of them. You can do normalized cross correlation, okay, or sum of absolute difference, or whatever. There are different ways in which you can compare or identify whether these two are identical or different, how different they are. Okay, you can apply any of them to identify which is corresponding points. So now I will show some of the slides to visualize you better, okay, on these details. If you have any quick questions, you can ask before I start that discussion.
So this last thing, total computations, is for entire image, right?
Correct. It is for the
image to image.
Right. Correct. So identifying the depth information of a scene, okay, from two images.
And so this disparity range, it will always be given, or?
No, not necessarily given. It's in fact, it is a design criteria. So if we roughly know the depth information and the camera focal length and the baseline, we need to calculate ourselves. If they don't give, okay, we can, based on looking at left and right images, okay, we can make a guess. What is the extreme disparity that the point has, that we can see and make a guess. In the worst case, it is it goes from here to here, minus the all through. Okay, any other questions? Okay, so then let me share some of the slides and discuss. Okay, so I am taking the information in these slides from Professor Mubarak Shah video lectures, as well as Professor Jitendra Malik video lectures. He is also a professor at UC Berkeley. He is professor at UC Berkeley. Professor Jitendra Malik is professor at UC Berkeley. And Mubarak Shah is at University of British Columbia, I think. You can check. Yeah. So essentially, this is the scenario for depth information. There are several sensors that gives the depth. So they give the 3D information. Most of them give sparse 3D information. In the sense, to extract the 3D information, what they do is, instead of having the two cameras, they will have a camera and a projector. The advantage of having projector is that, so they know pinpointedly where the, it's a laser projector. So we know pinpointedly where say in the left image, like instead of left image, we know where exactly we are projecting which scene point. And the camera captures exactly reflection of that scene point. So for each projected point, I know where exactly the projection in the image. So I can easily compute the disparity. That is the idea of using projector or even the IR based projectors. So you can see here, this is the basic principle of depth extraction. So if there are, say, object, say initially the projector is looking at a point A, that means the object is of height h. Okay, then its projection gets formed at A1. And if the object is not there, if you are looking at the reference point, or if you are reference plane, then the projection gets formed at B. That means when the object being there, not being there, has its projections at different locations. Okay, using this difference, that is disparity in our case, we can identify the depth of the object. Okay, using this triangulation principle, just use the similar triangles approach. Okay, and then we can calculate that h equal to x by tan theta. X is this, okay, and theta is this, and then h is this. This is h and this is x. So you know that tan theta can be easily computed like this, and h can be computed like this. The challenge in stereo is how do we find out the disparity, because these two happens in two different images. That means it is not ideally the case with object and without object. Okay, this is the case when the there are two cameras which are looking at the same object from different positions. Okay, so this is he is Professor Jitendra Malik. He in his video lectures also you can see the description of this. So as I mentioned, the scene point, okay, is seen by left eye, and usually pinhole camera model is what is assumed. Pinhole camera model means the rays of the object or the scene pass through this pinhole and gets its image formed behind the camera in an inverted fashion, or in front of the camera in a like without inversion. Okay, so as you can see here in this, these are the pinhole cameras. Okay, and then the image gets formed, okay, at the focal length distance in a straight manner without inversion at the image planes. Okay, image planes are 2D planes and the scene is in 3D. So you have the reference coordinates in 3D and then the image coordinates in 2D. So that transformations are required usually when we want to identify, say, make the calibration essentially. What is each pixel corresponds to in in terms of XY. Okay, each pixel corresponds to what mm or centimeters. Also in terms of depth, each pixel corresponds to how many centimeters or mm. So this is the same thing that we have discussed. I will skip the derivation because we have seen before. Okay, and then as I mentioned, there is there can be a projector in place of the camera, second camera, or there can be cameras itself. When there is a projector, that is active light used to identify the correspondence, okay, the job becomes easier, and such methods are called active stereo methods or active methods. Active methods are there where we use the light information, structured light information, okay, to find out the depth information. So as I mentioned, the epipolar plane is the plane that connects the scene point with the camera cameras. So you can see that these 3 points, okay, if you define a plane connecting these 3 points, okay, that is referred to as epipolar plane. And what happens usually is if you form an epipolar plane, any of the scene point, okay, if you see, okay, its projection in left image or right image left image will be there only at the on the corresponding epipolar line. Epipolar line is the line that crosses, or that is the that intersects the epipolar plane with the image plane. Okay, so you can see any of these scene points, all these scene points will have a single projection here, but it will have at different disparities, okay, at different locations in XR. That's where the depth differs. Okay, so if we assume that these cameras are placed horizontally, then the epipolar lines are also horizontal. If we don't assume that, make that assumption, or if it is general setting, then what happens is the epipolar plane cuts the epipolar lines, not necessarily in horizontal manner. Okay, they can be like this, like this. Okay, in such case, what we need to do is we need to first rectify or make the epipolar lines horizontal. Okay, using some of the camera geometry. That is referred to as image rectification. That is the first step, in fact, while doing the establishing correspondence or recognizing 3D. Because what happens is camera position is not always in our hands. They may be positioned like this or positioned like this and so on. So, but however, we can find out the epipolar lines and through camera geometry, we can make them horizontal. Okay, and that is referred to as image rectification. Okay, so I am skipping some of the details. So you can consider if cameras are differently oriented, you also need to understand the rotation and translation matrices between the cameras and between the two cameras. Okay, as I mentioned, this process of making this horizontal epipolar lines being horizontal is referred to as rectification. And this is the first step, in fact, in stereo, because this will limit the search only to the one dimension rather than searching for any key point or any point in all across two dimensions. Otherwise, we have to search for each y and each u and each v. Okay, as we mentioned, a scene point, if we would like to find out the corresponding point, we will search on the same horizontal line if the epipolar lines are aligned horizontally. Okay, and then we see the distance, okay, of the patch here versus all these patches. The patch may be represented by features, and hence we can find the feature distance instead of finding the pixel based distance. That is also absolutely fine. In fact, we can also find out, say, pixel distance, okay, from this patch to this patch, feature distance, that is gradient distance or HOG distance, and so on, this patch to this patch, and a combination of them also is fine. Wherever the patch matches, the distance will be lower. That minimum is referred to as it is the location. The shift between this and this is called disparity. The location is not called disparity. Please make a note of it. Okay, this may be at 100, 120. This may be at 100, 122. So 122 is not disparity. 122 minus 120, that is 2 is disparity. Okay, hope you got the point. Also, then you can find actually the sum of square difference based optimization to find out the corresponding point, or sum of absolute distance based minimization, or cross correlation based maximization, or normalized cross correlation based maximization. Okay, or many other ways, mutual information based maximization, and so on. Okay, so you can use any of these methods, and you can also use any of the features, not necessarily even the pixel information, as I mentioned. Okay, you can also formulate a little bit of probabilities and use them. Also, usually, as I mentioned, to find out the correspondence, we use the patch-based similarity, not the pixel-based similarity. Okay, so this is in fact used even in not only in stereo. It is also used in optical flow. It is also used in, say, compression, image compression, video compression, in many video compression mainly, and so on. Okay, so this is widely well known, finding correspondence and finding out the similarity points. As we discussed, it is quite common for all the computer vision tasks. So explicit expression, as we discussed and written, this can be written in this way. Okay, and what we are trying to do is minimize with respect to 2, here with respect to u and v. Okay, so both u and v are also functions of x comma y, as we have noted before. Because at each x comma y, the u and v may differ. If they are aligned, u is 0 for all, but v will differ from each of the x comma y. So that finally an image with all u or all v is referred to as disparity map. What we see, the depth information, okay, we can't readily see the depth information without calibration. That means identifying the baseline distance, okay, and as well as the focal length, and using the calibration, we cannot directly write the depth. What we display and show is the u comma v or the v image, or disparity image. So these are all different expressions as we discussed to find out the disparity. Also, you can see this. So this is how say if this is the disparity image, this is left image and this is the right image, and then this is the disparity image. You can see that here the disparity is high. Okay, that means there is a depth information here. Remaining all have 0 depth. Okay, this was very old publication, so you can see the results in this way. Okay, of course, there are several methods to find out the disparity. So one of the previously well-known method is by simulated annealing. That is done like simulated annealing is an optimization technique. It is in fact a very nice optimization technique. Okay, so what usually done for extracting the depth information or disparate information is not only to use this cost function, but also to use a additional regularization function. That means, say, what we assume in any scene point, the depth from disparity from one point to other point, next point doesn't vary too much. Okay, we assume that the disparity varies only slightly from point to point. Given that, what we assume is the disparity is smooth. Okay, that's an additional constraint that is also used in optimization. So that each point will not independently decide its disparity value from the neighboring value. Okay, I will skip the details of simulated annealing. This is an optimization technique to find out, to minimize this such kind of cost functions. Okay, and then I will show some of the results. The previous experiments for generating the synthetic data was like real data with depth annotation is very difficult, because at each point you have to identify what the depth information is and provide it as the reference. Okay, for checking the methods or verifying the methods. So people, what they used to do is they used to create random dots. Okay, these random dots and these random dots, if you see, this region is being displayed in these random dots by this height. Okay, by this shift. And they will fill the like left out random dots with the random dots again. Okay, and then they also see with red and green goggles. In 3D movies and so on, you will be given red and green goggles, right? So red and blue or red and green. What will happen is the one of the image in that color image, red and green images, if you see, they are displaced images. They are not the actual images. So when you see with the Google, what happens, through one eye, you will only get red image information. Through another Google, you will get only green image information. When you blend them, what will happen? You are able to see the depth, perceive the depth much better. Okay, so that's why the 3D movies all use red and green or red and blue goggles. Then you can see easily the depth information there. Okay, so you perceive as if even from 2D blend of images, one image with red, okay, and one shifted image with green. Okay, if you blend them and put in a color image, you can see perceive the depth information, because you are seeing as if you are seeing from the images in the natural scene. Okay, so as I mentioned, the disparity map, V map is what is shown here. V at each x comma v is what is shown here. As you can see, this is very closer, so higher depth, say, or you can consider with respect to reference, higher depth. Okay, this is the next higher depth, and this is zero depth. Okay, that you can see here. And usually people try to see how best they can do compared to the ground truth. Okay, in terms of estimating the disparities. That imply that estimating the ground truth as well. So as I mentioned, they will first establish their methods with random dot images, okay, to estimate the depth, and then subsequently they will demonstrate on the natural images. So if you have any question now, you can ask. Okay, so otherwise what we do is we will conclude the class with this now, and this is the this more or less concludes the discussions on computer vision topics, okay, along with the fundamentals that are required to understand the machine learning or deep learning as well. So from the next class as well onwards, we will start the discussion on the neural networks, and then deep neural networks and convolutional networks and other deep learning methods for computer vision. Thank you.